Energy systems are broad. We can talk about it in different ways, looking at it from heating, ventilation, air conditions. They're all energy systems. And we know what energy is. We have energy. Energy is something that it is said that it cannot be created and also cannot be destroyed, but can be changed from one form to another. That's what energy is. So whatever energy you have now that you're using was in another form. So for you to use it for whatever you want to use it for, you need to identify the form that you're going to convert it from to another. And that's what happens in the renewables as well. The energy in the wind is transformed into electric energy. The energy in the sun is transformed into electrical energy. I use these two because these are the two major energy sources that I'm going to be looking at because uh, I divide this into two. The energy from the sun, converting it into electrical energy, goes through a chemical process. The energy from the wind, converting it into electricity, goes through a mechanical process. And we can divide it along that line. We have the energy storage system, where we convert chemical energy as well into electrical energy. We have other forms of renewables like the tidal, the wave energy system. We have the geothermal system. We have the biomass system. Most of them is converting a form of energy into electrical energy. I understand most of you are mechanical engineers, but we're going to be talking things a bit electrical today. So the focus is looking at how we harness this energy system because uh, the world is becoming global and everything that we are doing, we need energy to be very important in a dynamic world. I'll see. Sorry. Okay. So I've got some learning outcomes. We are students. So there are things I would expect that at the end of this presentation, we will be able to know if we have not known it before. If we know it, we'll be able to understand it better. And the first is understanding the difference between design, modeling, and modeling of energy systems. Now, I would by engineering design. Can anybody give me an answer? What do you understand by engineering design? I said I'll make this session a bit. I wouldn't want to just be doing the talking and talking and talking and talking. I want us to interact engineering design. Is there any difference between engineering design and modeling of energy systems or modeling of engineering systems? Is there any difference? Because a lot of times you could see journal articles out there that would say design and simulation, modeling and simulation. Are they talking about the same thing or not? We'll get to know that as we get along. The second thing we'll look at is understanding what it means to optimize an energy system. So what we're looking at is what is optimization? That's going to be where we're going to narrow the discussion to. What is optimization? Why should we optimize? Is optimization necessary? When we design and model the system can work. So why do we talk about optimizing it? Is it not going to be too much trouble? What are the benefits of optimizing? So these are the things then we would try to identify the different types of optimization methods. Now, there are various types of optimization methods. And we would need to identify them specifically because you need to know which method would apply to you in which method will be best. You can have two methods like using linear programming or using a heuristic method.
Uh,
Am I muted? Can you hear me?
Yes, we can hear you.
yes, you're
Okay. Okay, that's all right. Okay. So we'd like to identify the different types. I want you at the end of this presentation to be able to identify the different types of optimization methods. And also, I try to avoid modeling of optimization problems because if I go into that, that would be too broad. The three things that we are looking at here, which is design, modeling, and optimization, are topics that could be treated independently, individually. They could be treated and looked at individually, and it's going to be a broad discussion. So here we're trying to put these three together and discuss it in one seminar. There'll be a lot of uh, crushing and trying to compress it so that we can understand it. Okay, and sorry. Oh, I'm sorry. Just hold on. Yeah. So we'll also look at the application of optimization techniques for efficient operation of renewable energy systems. So that's what I want you to know at the end of this, the application of optimization techniques for efficient operation of renewable energy systems. So we'll just look at what does an optimizer do actually, because it's all about efficiency. I'll give you a little analysis. I was reading through the United Kingdom energy report, and they have it that as at 1975, they had a lesser population than they have today, but they are consuming less energy today than they consumed in 1975. The population increased, but the energy consumption reduced. What do you think has happened within these 45 years? What do you think has happened? It's all about energy efficiency. They have things now that consume less energy than it used to consume in the past. So energy efficiency has come into play. And for us to operate our system efficiently, we need to optimize. So this is an aspect we will be looking at. Okay, so we look at some basic definitions. The picture on the right, it's on my right, it's just a sample of a tidal turbine that's rotating, and it shows how the tide goes twice in a day. In the morning, the tide comes in, and in the evening, it goes out, and it generates electricity as the tide goes in and out. Irene seems to be is an expert in this area because she does a lot of hydrodynamics, so she understands a lot how this happens. Okay. So the first thing we'll define here is engineering design. I did ask the question, nobody, don't be scared. There's no wrong answer. There's absolutely no wrong answer. All answers are correct. They're subject to defense in a way. When you give an answer, you just need to be ready to defend the answer. There's absolutely no wrong answer in anything you're discussing. It might not be right in a specific perspective, but it's not wrong entirely. So don't be scared. You just have to say so. Engineering design is a method that engineers use to identify and solve problems. So what does that mean? For you to carry out a design, you must identify a problem, and then you go ahead to try to solve the problem. And that's the design process. For example, you need a car because you take a long walk, you want to get to your destination faster. That's a problem. Time. You try to design something. We move from designing uh, uh, we had a time in the world where they were using the cat and the horse, and that's the system. And we moved into building engines and all that. And now cars have become more efficient. Today we have electric cars. This is what engineers do. They design and they solve problems. So a method that is used to identify this problem and solve them is simply known as engineering design. This is very simple definition. If you want to go into the details of engineering design, there's a lot of things we could look at. Sorry. So then modeling. What is modeling? Because these two things are things that have been used interchangeably, and the aim of this seminar is to create a clear distinction between two of them. Modeling involves making representation of something. It is not a science, but an art. It's an art. You can only model something you know. Now, if you go back to engineering design, engineering design does not tell you that you must know it. You identify it, then you begin to make effort to solve it. For you to model something, you must have knowledge about what you're modeling. And so that's why you must design before modeling. Now, modeling is something that in the current day we are in, a lot of programmers model. So if you're a design engineer, you can design your work, look for a good modeler and work with the modeler, and he'll be able to model your design. Because when you model, that's when you can now improve on your design. So there's a way I want to look at it. It's a two-way thing. For you to model, you must have a design. Now, after modeling, you can test your design, and then you can now improve on your design. So there's a way to design, modeling, back to improving the design, then remodel, then before implementation. So we're looking at energy systems. An energy system is a system primarily designed to supply energy. That's what it does. Supplies energy service to end users. I did not specify what type of energy here because I'm looking at it. So if you look at that, an electrical energy system would be an energy system that is primarily designed to supply electrical energy services to end users. If you want to look at any other energy systems, what it will do is to primarily supply that type of energy to whoever needs it. And that's what energy systems are. Sorry, I'm clicking the wrong one. So then we look at energy management system. Why I brought in energy, I've not spoken about energy management systems since we started, but this is the bane of optimization. And this is the area we're going to be focused in this presentation. Energy management system and optimization. But I need to give you a brief review of some of the steps that will lead us. You can't just begin to build an energy management system or optimize an energy system. You must first of all have clear understanding of certain things that could lead there. And that's why we're coming from engineering design, modeling, understanding what an energy system is, and then we look at what an energy management system is. An energy management system, popularly called EMS in most cases, are automation systems that collect energy measurement data from the field and making it available to users through graphics, online monitoring tools, and energy quality analyzers, thus enabling the management of energy resources. So what does an EMS do? It sits between different energy sources. So if you've got 5 different energy systems. Let me come out a bit from the renewables and look at the conventional system. We have a gas turbine, we have a diesel generator, and we have a coal-fired plant. These are three different types of conventional energy systems using different types of fuel systems, though they are all thermal systems. Now, an energy management system can sit in between this and decide which source to be used at every point in time, depending on the load. So we want to meet a load. And you look at these three systems. The gas turbine works more efficiently when it is operating at about 80% and above. The diesel generator will work efficiently when it is working below 50%. It gives you lower cost. The coal-fired plant could be working properly when it is about 50, 60%. So we are looking at the load. The energy management system looks at the load and decides which source should power the load at every point in time. That's what it does. It's managing the system efficiently to minimize and reduce cost of operation. Now, the idea is when it does that, how does it change from one turbine to the other? And that's where optimization comes in. Optimization helps it do that because you wouldn't just start, for example, if the load is at 100% and you're running on a gas turbine, for example, and suddenly the load drops below 50%. What happens? Would you just immediately shut down the uh, the the uh, the gas turbine and begin to use the diesel generators? How would that happen? The optimizer does all of that for you. And that's why you need to understand the modeling. Then you bring in the energy management system, and then the optimization comes in to solve the problems. I think the last definition would be optimization. Optimization is a process of making something as good or as effective as possible. So in energy systems, we look at three things. We want to reduce cost. We want to reduce our energy consumption, so making it more efficient. And we also want to minimize cost. So there's a difference between reducing cost and minimizing cost. Reducing cost will be applied to me, the consumer. I am the consumer. I am paying for electricity. I want to minimize the cost I would pay for electricity. For the operator of the system, he wants to reduce its cost of generating electricity. So we have these three networks put together. You want to minimize cost, you want to reduce energy consumption, and you want to minimize cost. These three things put together is what the optimizer would do. So let's look at the different types of renewable energy systems and do a bit of explanation of how they operate so that we can now look at the modeling aspect. We have four main systems, and in this little picture down here, we have a wind turbine system, we have the solar system, we have the biomass system, and we have the hydro or water-related systems. Water-related systems, we've got tidal turbines, we've got wave energy converters, we've got hydro power plants. All that they are all water-related power generating systems, all fall within the water systems. I'll look at about four of them here and then go ahead to describe just two. So we have the solar power system. We know what the solar power system, this is just converting energy from the sun to electrical energy. And our focus would be the solar PV systems because there's a solar thermal system where we use the sun to generate heat and use the heat to drive a turbine to generate electricity. So that's another system. And the solar energy system produces direct current voltage because it has no rotating parts. And so wear and tear is something that is protected in this system because there's no rotating part, so there's no friction going on as it rotates. So that would keep the system safe. So we look at how does the sun generate its power? So the sun, the power from the PV would give this equation is what is used to generate power from the PV panel. And if you look at it clearly, it's a model. This is how models are developed. You look at the solar panel and then you begin to develop the model. And normally it's called a mathematical model. PPV is equal to APV is equal to IRPV and NPV. What this represents, this is the area of the PV panel. This is the irradiation, so the radiation that falls on the PV panel, and then this is the efficiency of the panel. That's the three main components. But all these components, so the main thing is the area of the panel and the radiation of the sun. Those are the two things that's considered in order to generate power from the PV system. Now, the efficiency is very important. And how is this efficiency defined? We have a second equation that defines the efficiency of the panel because you could have a particular area and a particular irradiation, and by the time you put them together to give you a good number, but by the time you now actually measure what comes out of the PV panel, it is far, far, far short of that. What's the reason? The efficiency of the system. And the efficiency is defined here using this equation. This is the derating factor. Then you have the actual radiation you get at the time of measurement. Then you get the standard test condition radiation, which is normally 1000 watts per meter square. So you use that. Then you have alpha, which is the temperature coefficient. I would explain this a bit, which is the temperature coefficient. And then you have the actual temperature at the time. And then you also have the standard test temperature. Normally, the standard temperature for a PV system is 25 degrees. So once you begin to get a temperature above 25 degrees, be rest assured that the efficiency of the PV system begins to drop. That's where your efficiency of the PV system begins to drop. So you'll be very surprised that if you put the same size of PV system in Indonesia and put the same size of same PV system in the UK during the summer period, during the summer period, you'll be surprised that the one in the UK will be generating more power than the one placed in Indonesia. What will be the reason? Maybe during the summer in Indonesia, you're getting 30, 35 degrees temperature. In the UK, they are hardly seeing 20 degrees, 20, 22 degrees. So which is below the standard test. So the efficiency of the turbine would be, of the PV panel would be higher here. And so it will give them more power than having it in Indonesia. Now, this is a subject of many research. A lot of researchers are going into trying to develop systems, cooling systems that will create automatic cooling system for the solar panel, such that it can be able to bring down the TPV to be as close as possible to the standard temperature that is required to run the turbine. So many researches going on in that area. So we have the wind energy system. This is a big subject of controversy because a lot of people don't even want it. That's why you don't find it in so many countries, because they feel that it defaces the environment. Having this three wind, this thing rotating all the time is not as beautiful as people would presume it should be. So it's a subject, and it's a rotating system. It can produce AC or DC depending on the converter system that is used. But generally, because it is rotating and it has a rotating magnetic field, the output power of a wind turbine would be AC. But because the fuel, what drives the turbine, is something that is not controlled by you, it's not controlled by me, it is nature. We do not know what the wind speed keeps changing with time. So the AC power produced from the turbine would be fluctuating. And so we have what is called the maximum power point tracking, and then you convert that AC to DC, and then convert that DC back to AC in order to get a smooth power out of the turbine. This process has a lot of losses as well. We'll look at the equation that produces the wind power. Sorry, checking. So for the wind operation and that of the tidal operation and that of the hydro turbine are all the same because they are all working on rotating system. So they have very similar system. So you have the density of air. That's going to be the main difference between this and the hydro and that of the tidal system. Those will be looking at the density of water. And you know, water is far more dense than air. And that's why you can see your water, but you cannot see the air. You can only feel it. So for the wind turbine, you have the density, you have the power coefficient, and because it is rotating in a circle, you have pi. You have the radius, and you have this velocity, which is the speed, the actual speed. And then you also have the efficiency of the turbine. This is what is considered. In designing the wind turbine, there are certain stages that they look at. One of the stages you look at is what they call the cut-in wind speed, and they also have the cut-out wind speed, and they have the operating wind speed. So you could have a wind turbine and the wind is at certain level, but it is not generating power because it is not up to the cut-in wind speed. There's a way the wind will be high, there's a level it will get to, and it will not be generating. Though you see, you'll be very surprised. You'll be feeling, oh, there's so much wind, but the turbine will not be generating because it is not designed to stand that kind of wind. So it will just lock itself and stop operating. That's the way the wind turbine is. We have the hydro system, and the hydro system uses water just in place of wind to drive a turbine and generate electricity. We have the geothermal system. The geothermal energy system takes heat from the earth crust and brings it out, and it can be used to drive a turbine. It can be used for many things, but we'll focus on what we are interested in is in generating electricity. So we can use geothermal system. It's also renewable. It is clean, and it comes naturally from the earth. We have the tidal energy system. If you look at the tidal system, it looks exactly like the wind turbine, but it sits underwater. There are different shapes of it, different designs of the tidal stream, but you need to identify the location where the tide rises and falls for you to place the turbine, and it will rotate the turbine as the tide rises and falls twice a day. So the tide is very predictable. What you cannot predict about the tide is the intensity of the tide, but you can predict when the tide rises and when the tide falls throughout the year. It is highly predictable. So this is the equation for the tidal turbine. So if you look at the equation for the tidal turbine and you look at the equation for the wind turbine, you would see that they are closely related. Biomass. We all know what biomass is. That's another source of renewable energy. These are the 6 main sources of renewable energy. There's the wave energy converters, that's also renewable. And if I may ask, to make it a bit interactive so that I don't just keep talking, is a nuclear energy power station a renewable energy station? Can somebody just give me that answer? A nuclear energy station, is it a renewable energy system?
Marvin,
Yeah.
is the questions only for students or lecturers can also answer?
Students should answer.
Oh, students. Oh, I'm sorry. So I cannot give the questions to other people then. Okay, students, you hear from Marvin. So it's time for you to answer. Yeah. Okay.
I want to answer.
Okay. Just say your name. Say your name.
Power system is. Oh,
say
I'm sorry. My name is Avicenna.
Okay, Avicenna.
My name is Avicenna. I'm from Pen, Surabaya. I've heard that nuclear power station is one of the renewable energy source because I've heard that the fuel of nuclear power station is it can be used after it has been used. Like, I'm sorry, I can explain it.
No, yeah, that's all right. I've gotten the point. I got the point. Any other person? Can any other person answer? I got a point there. That's if you have an alternative view from what he has said. He said it is renewable. So if you have an alternative view, and he has given his reason why he thinks the nuclear power station is renewable. So if you have an alternative view, you can give your alternative view and we'll know why, and then we can compare the two and then give a clear-cut understanding of what it is. Because in the talks about the conventional power system and the effect on the environment, people don't talk about the nuclear power plant. So a lot of confusion is there. People do ask this question, where do they stand? Are they with the renewables or they are with the conventional system? So this has been a cause of, when you read some documents, you don't get clarity. People just talk about the nuclear system just the way it is. So we really need to, I said I'll use this seminar to clarify, to see if students on this side would understand this or know this, so we can, clarify it once and for all. If that's all you take from this seminar, it's a plus for me. Any other view? Okay, I'll answer the question. The nuclear power plant, it's non-renewable because the nuclear reactors makes use of uranium. Uranium is a source of energy, but it is not renewable. It is produced and it is buried under the ground. And that's why they don't build nuclear stations in and everywhere. Most nuclear power stations are built very close to the sea, where they have to store these uraniums under the water for cooling, because if it begins to explode, it's an issue. Now, the fact is that the nuclear power station is non-renewable, but it is clean. And so that's why in the talk about reducing carbon capture on the earth and all that, and trying to turn down the conventional power system, they tend to allow the nuclear power system to function. Though it's expensive to build, it's expensive to maintain, but it lasts thousands of years. But it's a non-renewable system. You need to know that, but the fact is, it is a clean energy system. So it does not mess up the environment like your diesel generators, like your gas turbines, like your coal-fired plants. Correct? So if you had an idea that it is a renewable energy system, it is a non-renewable energy system, but it is clean. So it has a component that the renewable energy systems have. So if you can always have available this thing for it, it is a proper system to use. But it's got its damages, it got its issues. The issues it has to do with safety. So you must be ready to preserve the uranium in a very safe way to continue to produce the nuclear energy. We go next. Now, energy storage. I added the energy storage just the last minute of this presentation because I looked at it. We're talking about renewable energy. We are not in control of the fuel that the renewable energy uses. It's nature. We cannot tell when we will have sun and when we will not have sun, although we can predict it. And so it is better. And then there are sometimes you have excess sunlight and then you just produce energy and it's wasting. So we need to have something that we can store our excess energy and use it. So for example, for a solar powered system, you know that during the night, you don't have any solar. You have solar power during the day, maybe from 10 a.m. in the morning down to 4, 5 p.m. in the evening. So if you can generate more than what you need, you store it. And once the solar is down, you begin to use the storage rather than going back to the conventional system. The energy storage serves a lot of functions, and we would see what those functions are from the generating part to the transmission part to the distribution part and down to the consumer. So for the generation, this is what the energy storage does. What's called AGC could be also known as fast frequency response. So it's automatic generation control. So we know that when load begins to change, when you're generating power and load begins to rise and fall, for example, in a conventional system, there's what is known as the ramp up time and the ramp down time of generators. So generators don't just ramp up. So if the load changes very fast, the storage system can act as a fast frequency response, so it can cover up for the load increase for the period while the generators are ramping up. So it does that. It does primary frequency control, which is what I've just described. You know, power has to be run at a certain frequency. I don't know what frequency Indonesia runs on, but here in the UK, we run on a 50 hertz frequency. So once the frequency begins to drop below 50 hertz, there is problem. And so the energy storage system is used to cover up this. So once the system is getting overloaded, the frequency begins to drop. As the frequency drops, the energy storage system can respond very fast and cover up and take the frequency back to normal, save the time when the conventional generators would ramp up. So it reduces abandoned electricity. I explained that when we're talking about the solar panel. When you have excess solar, instead of dumping it, you store it in your storage. It smooths fluctuation. So you see, for renewable energy systems, we don't have a control. We have lots of fluctuations. The energy storage system can come in to manage those fluctuations. All of this has to be done in a very optimal way. And that's why we talk about optimization. You can also use it to track generation plan. For transmission system, it also does frequency regulation for ancillary services. It does power supply, which is supply the power when the transmission system is weak. It does peak load shifting. And when you say peak load shifting, for systems that have got kind of a tariff model, you've got a tariff model, and maybe in the middle of the night, you've got low tariff, and during the day, you've got higher tariff. So if you charge your battery at night, during the day, you can now do a bit of peak load shifting. So instead of you can decide that, okay, my energy storage would supply 10% or 20% of the load, while the remaining 80% should be what would come from the conventional system. and that reduces your energy tariff. For the distribution side, it saves electric power application and installation charges, peak to valley arbitrage, demand response. So that's like fast frequency response, improves power quality. Then it is used for an integrated energy market. That's another thing. So the energy storage in the new convention and new system we have, which is the renewable energy market, the energy storage is one of the most valuable component. It's one of the most valuable component. Right now, without this energy storage system, will still fall back to the conventional system. So the idea of reducing the climate change and all that might be a failed agenda if energy storage does not ramp up to meet up the challenge. Okay. So we'll look at design of renewable energy systems. I'll just talk about two designs because our time is already fast spent. I'll just talk about two designs here and I'll just go through that very fast. I wouldn't spend much time as I have spent earlier. To design a solar PV system, the following components are required. We'll just look at it. The PV module that converts the sunlight to electricity. The maximum power point tracker. I didn't talk so much about this, but what this does is to track maximum power from the PV system. If you look at the PV power curve, it goes round and there's a maximum point where it needs to power, where at every point in time, what is produced, you want to get the maximum out of it. It's a power electronic device. And what it does, it's just to track maximum power. You find this in every variable system, like the wind turbine, like the tidal systems, every renewable energy system where you cannot predict what the output it is at every point in time. It tracks the maximum power. It's a very important component in renewables. So we have the inverter, because the power that we use at home is AC. So if the PV generates DC, we need to convert that DC to AC, and that's what the inverter does. It's got solar PV sizing, very important. You can't just decide that when you want to design a solar PV system, what are the things you consider aside the components. Now, when you have identified these three components which I have listed here, now you want to design the system. You must consider what you're going to supply, the load. So the sizing, determine the power consumption demand. You must size the PV module to meet that demand. You must size the inverter. And then you must size the battery system, because we have come to agree that we need the battery system. These are the things that you need to size. There are different ways to size this. If you're interested in doing a research in this area, I would advise that you go and read about solar PV system sizing. And so you'll be able to know how sizing is carried out. There are a couple of equations. I tried not to put equations here that would help you in sizing the system. Once you're able to identify the range of the load you want to supply, then you can now decide the sizing, looking at some environmental issues, because you need to know, where am I placing this turbine? What's the solar irradiation in this area? For the past, maybe you get historical data for the past 5 years, and you see what the solar irradiation in that area has been in the last 5 years. That will be able to tell you the amount of power you can get out of the PV panel. And then this will lead you to knowing the exact size. There are softwares now that will do all of this. So once you have all the basic information, all you need to do is to input those information, and it will tell you the actual size. Funny enough, it can even tell you the type of PV system, because there are different types of models are designed, monocrystalline, polycrystalline systems. These are chemical components. There are softwares that will tell you the exact type you should use for a specific area based on the kind of sunlight or irradiation you have and the load pattern you have. It will tell you exactly the sizes. And once you apply that, you would get optimum efficiency. Solar charge controller. If you have a battery, you don't want to destroy your battery. That's one thing you don't want to destroy them. The batteries are very delicate issue. I could talk about batteries for very long because I've been studying batteries for a while. And in battery models, normally the manufacturer would tell you this battery should last you for say 10 years. But you could get into using that battery, and after 4 years, the battery dies. That means there are certain things the manufacturer may not have given you in details. If my battery will last for 10 years, there's a condition for which that battery has to be operated for it to last that 10 years. Anything below that could shorten the life of the battery. And so all of these are things that you can do within a design system and modeling and optimization. We'll look at the wind turbine system. And this is what the wind turbine system looks like in detail. So this is not just a turbine now. We'll look at the mechanical components in the wind turbine. We'll look at the direction of the wind. We'll look at the rotor, which is the blade that rotates, and the hub. Now I'll give you this. What's the difference? If someone can answer me this, I'll be very happy. What's the difference between the wind turbine and the fan in your house? What's the difference between the wind turbine and the fan in your house? They've got blades, they rotate.
I want to try to answer.
Okay.
Okay, my name is Lucky. I'm from Penn. I think the difference. Wait, can you hear my voice?
Yes, I can hear, but if you're louder, I would appreciate.
Okay, sir. I think the difference between the wind turbine and the fan in my house is if the wind turbine use the wind to rotate the turbine to create electricity, but the fan using electricity to rotate the blade. I think.
Okay. That's correct. That's the difference. The difference is this one uses the wind to generate electricity for use, while the fan in your house uses electricity to generate the wind or the breeze or what you have, the air that you have in your house. That's the main difference. If you look at both of them, the structure seems to be, if you look at a fan in your ceiling, it has 3 blades, just like the wind turbine. You also have wind turbines. What we have here is the vertical system, which is the most common wind turbine. You have the horizontal system wind turbine, which is not very common because of the energy efficiency of the horizontal wind turbine is quite low. So that's why people now go more for the vertical axis wind turbine. But the wind turbine has these few things. So the wind, as you can see, the wind comes in from here, hits the blade. As the blade rotates, the rotor, which is hidden inside the hub, rotates. And then it begins to work like any other generator, like your diesel generator. You know, your diesel generator, once you power it on, the rotor begins to rotate, it begins to generate alternating current. That is how this happens. But you know that the problem with this one is the diesel generator, once you start it, you operate at certain level, it continues at that level. But the difference here is the speed of the wind keeps changing. The speed of the wind keeps changing. And there are 2 things you need to note, which are, well, this is the equation that determines how it gets its cut in and cut out wind speed. Before we go to those 2 things, if you look at this equation, it's nothing different from the initial equation we've written, but what we have said is, in this case, you look at 0 here. Once the velocity is less than the cut-in velocity, there is no power production. At this point, once it is higher than the cut-out velocity, there's also no production. So the wind can work between these two points, where the cut-in wind speed, the velocity lies between the cut-in wind speed and the rated speed. There's a rated speed. So once the speed lies between these two, it generates electricity. And once it lies between the rated wind speed and the cut-out wind speed, it also generates electricity. But the power at which it generates is different. And that's why you have this equation. For this other equation, this is how it generates. For this one, this is what it generates. So it changes as long as the V is lying between this and this, or this and this, it produces power. Anytime it goes above this, so that means you can have a very massive wind speed, and yet your wind turbine is not producing. And you'll be surprised, oh, you could see an area by feasibility studies, the place has good wind speed, but yet you would have no power because the wind speed is damn too high, or you have to design a turbine that will match that kind of speed. It's important that this is known in your design system, because if you don't know it, you might design something that is very successful and useless. So the image here shows the basic components that go to make up the typical wind turbine system. And the power in the wind that is available for harvesting depends on both the wind speed, which is coming from this direction, and the area swept by the rotating turbine. And that's why when you see offshore wind turbines, they have very large blades. If you've not seen a wind turbine before, not the one standing, if you've gone to like where they test wind turbine blades, to see the length of the blade, as you see it so high, you might think those blades are short. Some are up to 10, 15 meters long, because the area swept by the blade determines the amount of energy that can be harvested from the wind turbine. So let's look at the modeling. So what's energy modeling? By definition, energy modeling or energy system modeling is a process of building computer models of energy systems in order to analyze them. Energy models employ scenario-based analysis to investigate different assumptions about the technical and economic condition at play. Now, this is what I like to explain. This is quite exciting, because this is once you have concluded the design, now you want to play with the system. You want to test the system. You want to try to look at how sustainable your system is. You use computer models. Like I told you, it's an art. The design aspect is core engineering. You must have engineering knowledge to be able to design an energy system. But the modeling aspect, anybody can model. Anybody can model. All he needs is information about the design, and he'll be able to model. And then we model because we want to test different scenarios. Like we talked about the wind speed. We talked about the operating wind speed lying between the cut-in wind speed and the rated wind speed. We also talked about it lying between the rated wind speed and the cut-out wind speed. So once it is operating at this condition, so when we want to test in a model, when you want to test it, you can begin to adjust the operating wind speed, and you would get to the point you would see where the turbine would fail in your model, in your computer model. You don't need to go and to test this, and then when it crashes, the entire resources that was spent to build that turbine is at waste. Recently, if you follow what's happening in America, I think one of the space rocket, unmanned space rocket was launched, and as soon as it took off, it exploded. That kind of system is that design was modeled. Maybe they tested it to an extent, but when the conditions changed and went beyond the limit of the test or the scenarios which they considered, the rocket came down. Although nobody died because it was an unmanned rocket, but if people were inside, they would have lost everybody inside. That's the importance of modeling. Classification of models in power systems, because what we are focused on now is renewable energy generation. So we have electricity sector, we have system operational models, and we have power system simulations. Now, what's an electricity model? The power, you design the output and put all that together. That simply gives you the electricity sector model. So if you're looking at a system, say a microgrid system, and you model the microgrid, that's the electricity sector model. If you're looking at a standalone system and you model that system, that's the electricity model. That has nothing to do with the operations. After you have modeled that, you now have to move into the operational model. How do I want the system to operate? You begin to develop that within the model. And then the next, you look at the power system simulation. So you can simulate that model. In the course of simulation, you can make changes. You can make changes. And these three things in power system is highly considered when modeling a power system. The modeling and analysis tool includes long-term capacity expansion. So you look at, I talked about expansion. So you can, in modeling, you can look at, okay, how do I increase the system? If you have done a bit of forecasting and you have an idea of how the load is going to increase with time, so with the models, you can begin to change and okay, after 5 years, this is what we're going to do. So it's an in-house system. This plat is a kind of a software that you can use to do long-term capacity expansion. So if you follow it very well, you would be able to sustain energy continuously because you would plan your expansion according to your predictions. And there's no time you would, in most developing countries today, we don't have a constant power supply. And it's because we don't have good models. So we don't have long-term capacity expansion. So in the long run, we have energy generating today and it meets our load. Suddenly the load goes so high and then we cannot meet the load anymore because we don't have a flat system for modeling, for planning. So you have unit commitment and dispatch. Unit commitment and dispatch, in most cases, does not apply in renewable energy system. But if you look at a microgrid that is grid connected, you can look at unit commitment and dispatch. Dispatch is fine, but unit commitment mostly works with conventional system because you have to commit the most economic system at a time. So when you bring in energy storage, smart grid, system flexibility assessment, these are things you do when modeling. Modeling is broad. So you have operational planning, grid integration studies. All these are done within modeling. When you're doing operational planning, grid integration studies, all these are done within modeling. Energy models are usually intended to contribute to system operation. I put the red, engineering design or energy policy development. Why I put engineering design is because we've talked about design before. And so I said, you can design, model, and then go back to redesign. So when you design a system and you model the system, you put the system to test, and you find out some things that you need to do more, you go back into design. So energy models could help you improve on your design. That's why I put the engineering design in red. So what we must understand the best way to supply energy for a reasonable demand. If you want to model, You must understand the best way to supply energy. Suitability of model depends on the goal of modeling. Data, software, availability, and competence of the modeler. So the model, like I said, modeling is an art there, and you can develop your competence in modeling depending on what you know. Model types: supply-based model, demand-based model, hybrid models. So when you look at supply-based models, what would that be? From the generation side, demand-based model from the demand side, hybrid models when you combine the two and model them together, or you have various energy systems being modeled. Those are hybrid models. Supply models, I'll just look at a bit of supply models. Demand-based models are very clear. You're just looking at the demand side management and modeling the demand side based on predictions and all. But for the supply-based model, this is an area that is a bit very important because you want security of supply. So there are accounting models, mainly based on database. So you have information. The database information could be past data gathered, predicted data, all put together. It is the status quo pattern. What would be the energy requirement in future? For you to do a sustainable supply-based model, you need to be able to tell what's going to happen in future. It's the most popularly used model. Long-range energy alternative planning, SLEAP. So you could develop an alternative just in case things change. What are we going to do? So you have the optimization models. So linear to non-linear optimization models. Develop a multi-period linear optimization model with stochastic and non-stochastic parameters, and combining generation and transmission. Can someone just tell me, what do you understand by stochastic models? Stochastic parameters. Because I don't just want to use words and then at the end of the day, we just stochastic parameters. What makes a parameter stochastic? If we can define stochastic, then we can tell what is non-stochastic. So non-stochastic, we can call that deterministic.
Is the questions for students, Marvin?
No, anybody can answer.
Or anybody? Okay. But I still want to give it to my students. Okay, students, please answer Marvin's question.
Excuse me, Guarini. I would like to answer this.
Okay, so please state your name first.
My name is Zhu from France. I believe previously on the lectures in college, the teachers never previously mentioned stochastic, but I did a quick research about stochastic, and it is something that has to do about a random probability distribution.
Random probability distribution, yeah?
Yes. So I guess that's from me. Thank you.
Okay. Correct. Random probability distribution. Why is it random? There are lots of uncertainties. There are things you don't know about it. And you model this into the system. You model these uncertainties into the system, and then it becomes stochastic. Non-stochastic is a determined data. You know exactly what it is. You know everything about it, so you can apply some. But when you're dealing with renewables, you know that it is a very deep stochastic system. You cannot tell what you are going to get the next minute. But you can model it with some level of uncertainty. And that's why you use predictive models. That's why you apply some predictions. And then you can also check your your errors, the difference. By the time if I predict tomorrow's load consumption, for example, at the end of tomorrow, I'll be able to tell the difference of what my prediction was and what we actually got tomorrow. And if I have those kind of prediction continuously, I can have kind of those random probability distribution. I can apply that to a model and use that to test a model. So we don't know exactly what we are dealing with, but we are managing it within an uncertainty range. If you take out the uncertainty, it becomes non-stochastic. That means you know exactly what you're dealing with. The market allocation model. I don't normally talk so much about the Merkel model because it's a different area of analysis. It has really nothing to do with the engineering design, but operators of a microgrid system or renewable energy system or a conventional energy system make use of these to look at the market on how they determine the cost of energy. And that's what they use this for. And it comes from the supply side, because if I'm supplying power, I need to know how much I'm going to sell my power at every point in time so that I make profit, so that I can get my return on investment. So we look at energy management objectives. The primary objective of energy management is security and stability of the system. That's the primary objective. Every other one is an add-on. If we have to achieve any other objective, that's a secondary or the tertiary objective, and we don't achieve security and stability of the system, then we have failed. The secondary objectives is economic operation and control. So we want to have security of supply, we want to have constant power supply, but we want to do this in an economic way so that it is cost effective, because that could help both the consumer. If I can do it in an economic way, I can reduce the cost of energy that the consumers will pay. Then the tertiary objective is the optimization, which is operational planning and maintenance. If you go into history and try to look at when people started optimizing things, it took time, because they needed to know, if we apply optimization, are we still going to have the system working as normal? Because if we begin to optimize and the system begins to fail, then the optimization isn't. That's why it's a tertiary objective. The main objective is for the system to continue running. The primary objective is to maintain the power system in a secure and stable operating state by continuously monitoring the power flowing in the lines and voltage magnitudes at the buses. That's the security. We want to monitor it. The energy management system does the monitoring and ensure that it is stable at all times. Maintaining the frequency within allowable limits. For example, you have a frequency of 50 hertz. What's the allowable limit? It can go up to 50.5 or 49.5. So the energy management system does ensure that the system operates within that range. Maintaining the tie line power close to the scheduled value. What's a scheduled value? So you want, at every point in time, you don't want to waste energy. You don't want to waste energy, because energy, if it is not stored, is wasted. Now that we have storage systems that we store excess energy, before now, when we didn't have that kind of a system, so if you require maybe 10 megawatt of load and you're producing 15 megawatts, the whole 5 megawatts generated is wasted. So the energy management system kind of comes in to manage this kind of situation, to ensure that what is generated at every point in time is very close to the scheduled value. Secondary objectives. The economic operation of the power system through real-time dispatch and control. So The secondary objective actually can help the primary objective in achieving, especially maintaining the tie line power, because you want to do that so much fuel, you don't want to on a generator that is not supposed to be on, so you run this in an economic way. Optimal control of the power system using both preventive and corrective control actions. Real-time economic dispatch through real power and reactive power control. That's the secondary objective. We'll look at the tertiary objective, what it entails as well. The tertiary objectives: optimization of the power system for normal and abnormal operating scenarios. Optimal control of the power system by appropriately using preventive and corrective control actions. Maintenance scheduling of generation and transmission system. Maintenance scheduling is very important. With proper optimization, you will be able to tell when to begin to maintain your system. You have a wind turbine, for example. With proper optimization, you can say, okay, every 5 years, we have to service the blade, we have to fix the rotor to ensure that it runs continuously for another 5 years. It's an optimal process that you can use to tell that. So we look at how the EMS evolved over time. When it started in the early 60s, it was termed as control centers. And what the control centers did was they were initially termed a load dispatch centers. So they were using it to manage just load, to monitor the load and know how to dispatch power to meet the different sets of load. Then by the 1970s, it evolved into what they called energy control centers. So the first one was managing power. The second time it began to manage energy. So here the main task was to control the energy rather than the power. And then in the 90s, it evolved into what we now have as the energy management system. So it's pretty new. And the EMS, the main task was to manage the energy through various techniques like load management, LM, demand side management, and distribution management system. There's a difference between DSM and DMS. The functions and benefits of the EMS. We have control functions, we have operating functions, and we have optimization functions. Then we have the planning function. We've had a little talk on the control, operating, optimization. Planning is just all about looking ahead and ensuring that we continue producing more economic systems, more cleaner energy systems to match up the demand for the future. Energy management control function. Real-time monitoring and control function. It does automatic control and automation of power systems like automated interference and electronic tagging. It does efficient and automatic generation control and load frequency control. It does optimal automatic generation and control across multiple areas. Then we have the energy management, the operating functions, which is economic and optimal operation of the generating system. And we have the efficient operator decision-making, improved quality of supply. So it's all about decision-making, the right decision to make at a particular time, and also improve the quality of supply. We also have then the optimization function, which is optimal utilization of the transmission network, power scheduling interchange between areas, optimal allocation of resources, immediate overview of the power generation interchange and reserves. So these are just the three main points, or the control function, the operating function, and the optimization function. So we'll look at the planning function. Improve quality of supply and system reliability. So you can do this ahead of time. forecasting of load and load patterns. So if you can predict or forecast your load and load patterns, then you can plan on how you meet up this load, and it will help your economic operation of the system. Generation scheduling based on load forecast and trading schedule. So you want to have a clear-cut plan. Trading is something that has to do with the power you sell, and in most cases now, because of the way the renewable energy operates, even as a consumer, you can also sell power. So you can have a solar panel in your house and you produce energy more than what you need, and you can sell to the grid. I don't know if that's applicable in Indonesia at the moment. In the UK, it's in most developing countries, it's not, but in the UK, it's available. But people have found out that it's not economical selling the power, it's economical storing it. So people would rather buy provide energy storage system and store their excess power and use it later than sell it to the grid. Maintaining reserves and committed transactions. So when you talk about maintaining reserve, because you have proper planning, you would know how to reserve, because you don't want to have a failed system. You don't want to. Security of supply is something that you want to be guaranteed. So if you have good reserves, if there's immediate peak load, you can always meet it, which is what we use the energy storage mostly for. Calculation of fuel consumption, production cost, and emission. So these are things that you do as well with the planning function. So I'll just have an image here of, this is, I'll call it a microgrid system. It has the wind turbine, it has solar powered system on the other side, it has thermal power station on the other side, it has factories, it has a hydro power station on this side and some commercial buildings on the other side. So if you look at the grid management system at the center, that's the energy management system, how it manages this entire system to ensure that it runs economically and follows all the planning schedule, the control, and everything is done from that center. From there, they can dispatch. From there, they know when to switch up the thermal plants and all that. It's so optimization objectives in energy systems. So I think we're going to be rounding up around here just to look at what optimization does. So I have a little picture here that tells the three things. The price you pay. So as a consumer, you reduce. Optimization can help you reduce the price you pay, which is the price optimization, which can be defined as the average unit price divided by the energy you consume. Energy consumption. So you decrease the number of energy we use. Remember at the beginning, I told you that if you look at the UK energy data, it says as at 1975, where they had a lower energy population, they were consuming more energy than they are consuming today. So they've been able to decrease their energy consumption using this type of optimization. These are objectives. Then the increased part says energy cost effectiveness. So this is to minimize the energy cost. I've listed these three before, and I decided to let's round up with this. So this is what optimization does for you, these three things in power system. So we can look at the techniques that are used in optimization. I'm not going to explain because I've taken loads of your time. We've been talking for almost 1 hour now. And power and energy management techniques for microgrid basically look at the optimization-based techniques. So we have all of these are different optimization-based techniques, and they're divided into two methods. We have approximate methods, and then we have exact mathematical methods of optimization. You could see artificial intelligence, heuristics. For me, I work basically on the exact mathematical models, and I am my interest is linear models. So you see mixed integer linear programming is what I like, because that's, for me, I think it gives me the best result in managing energy systems. But you can have a look at all of this. There's dynamic programming is new. There's non-linear systems, because you can use the mixed integer non-linear programming. It's quite very interesting. It could be taxing, but you have all of this as what is used as techniques for optimization. Any questions? And thank you for listening. So open for questions now, if we still have time.
Thank you, Marvin.
Yeah.
This is very good presentation and also very good knowledge for them. I'm sure that my students will be very happy to attend for this presentation, and then maybe they want to ask you for another presentation, maybe. I can see from their face, I can see from their face that they are very curious.
Yeah, this we try. I covered too many things within this. Like I said, design can be looked at individually, and then we look at it more detailed and give clearer understanding. But this was just an introduction, just to give you an overview. So quite a lot of things have been said, so you can pick up whatever you like. You don't need to do all of it. You can become a modeler. You can become an optimization expert. You can become a design engineer. You don't need to be three of them. Don't be a jack of all trade and master of none. You just pick an area and become a master of that point. If you're a good design engineer, you can work with a good modeler, and you people will come up with a good system. You can work with three different sets of people. You have people who are very good in the optimization aspect. You have people who are very good with the modeling, and you have people who are very good with the design. And if we put three of them together, then you get a good system. But it's just important for you to have an overview knowledge of all three of them.
Okay, Marvin, we got one question here.
Okay.
If you can see your chat, yeah. So this student write his question in the chat.
Where is the chat?
Can you see it?
Yeah, I can see. See. There are a couple of us. Okay. Just this last one. My name is Mohammed Faldi Otada. I want to ask you about the tidal power plant in Indonesia. In the NTT.
So NTT is the name of an area in Indonesia.
Okay, there will be a tidal barrage. Is it tidal barrage, not bridge? So that's a big tidal plant that will connect the two islands and above it by various vehicles. Okay, I understand what. So my question is how the design and modeling fit, and what makes the difference to the tidal power plant. Now, the tidal system I showed you in this presentation is not a tidal barrage. That's a tidal stream. So there are two different things. The tidal barrage is almost like the hydropower plant. I think in the EU area, they have just one, which is one that is in France. It's an expensive system to build. So your question here is, what they intend to do is create a bridge across that's connecting two islands, and under the bridge is the tidal barrage. So what they will do is, for the tidal barrage, you actually create the tide, just like you have head of water created in hydro system. It's unlike the tidal stream. The tidal stream, you make use of the natural tide. For tidal barrage, the design here is they build a system that will create the tide. So it's not a natural tide, but it's created from water as well. So it's a place where they have natural tide, but they don't want the tide to rise and fall. And the reason they are doing that, because I think it's because of the road construction. They must have done a feasibility study that that place might be easily overrun by water. So what they will do now is to make use of that excess water that might overrun that area to create the barrage, and then the effect of that barrage, there will be continuous tidal flow there when they create that barrage. So what they want to do is to install turbines in that barrage that will be generating electricity. I don't know if that's clear.
I think it's clear.
So that's what they are trying to do. So in order to control the water that will be in that area, once they create the barrage there to put across the bridge, there will be continuous tide. So instead of wasting the tide, what they intend to do now is to put the barrage, the turbine there to generate electricity. It's a different concept from the tidal streams. Tidal streams is relatively new, but tidal barrages have been old, but it was said to be very expensive to build, and it was not economical in terms of what the cost of electricity was at the time. And so people didn't really invest in it. The one that EDF owns in France is, I think that's the only one that's in the EU area. They rather went into other forms of energy.
Another question, Marvin.
Okay.
If you can see it in the chat.
Yeah, I can see that. Good afternoon from Indonesia. My name is Asap. I'm I can't pronounce the names very well. Forgive me for that. Talking about energy management system. Do you have any good example, stroke role model of any kind of industrial company plant example, etc. Sorry, that you have ever known or researched before? So if you look at energy management system as described, I tried to make it a very, very basic. There are loads of models for energy management systems. There are loads. I could send you some link if you want to see for industrial applications, because a lot of industries use energy management system. I'll give you a simple example. Simple home system, energy management system that is easily developed. Let me talk about heating, ventilation, and air conditioning. The energy management system that manages system within an environment. It could be an industrial. So what it does, it monitors the temperature of the environment. So you don't have to switch on the air conditioning or the heating of the system or the ventilation. Once the system sees that outside is bright and clear, it can pop the windows open and air comes in from outside. When it's getting cold, it can close. When it's getting too hot, it can put on the air conditioning system. So it manages the energy on its own. You could have some areas where, for electricity, where you walk into a room and the light comes on. You may have seen that before. And when you walk, when it senses your shadow has gone out, the light goes off on its own. You don't touch it. That's a kind of energy management system. Some are timed. You could see that on street lights on the road. Once it's evening and it's getting dark, the street lights come on. And once the day light comes in the morning, the street light goes off on its own. These are all different types of applications of energy management system.
Thank you. I think it's a very good answer. Any other question? Okay, there's another question.
There's another one here.
Yeah.
So I once watched a video on YouTube about an idea regarding solar panel. The idea is to build a massive solar panel on the Sahara Desert to supply a huge amount of electricity. I know that high temperature means lower power output, but considering that there will be a decent cooling system, as a researcher and an expert on renewable, what do you think about the idea and where do you stand on it? Okay, recently I got a mail from somebody who was talking about harsh environments, because we also, just as we have marine harsh environment, we have environments that is very hot. So they were looking at developing solar farms in very harsh environment in the Middle East, and the description they gave was very, very harsh. Temperatures above 50 degrees, and they have kind of hailstones and dust and all that, which could affect the production of solar PV. So we're studying that now. I and some of my friends just looking at it, trying to see what will be feasible, because as it stands, we are not seeing solar to be an option. They are talking about solar and wind because they have good wind speed. But if they have hailstones, It's not going to be good for wind turbines. The wind turbine is rotating and the stone is falling. How does that work? And then secondly, on the other one, you said you read something to build in the Sahara Desert. What they are trying to build in the Sahara Desert are not solar PV panels. They are not photovoltaics. They are solar concentrators. And so they want to extract the heat and use the heat just as you use the geothermal heat to drive turbines to generate electricity. Now, they don't need heat in those places. So you will not say they want to create a kind of this. So they want to use the heat from the solar thermal system to drive this thing. And it's a massive research that is going on. There have been no real success at the moment, but there are signs of success in the area. There are signs of there are successes in solar thermal projects, but building those massive ones in the Sahara has been a challenge, but it's still a subject of massive research. And with time, I think there will be a solution. Any other question?
One more question.
Did another one just come in? One or
Yes.
two? Okay, one. My name is Alfian Fami Mubarak from Class 3A. In regards to the topic of solar panel earlier, I have heard the term duck curve. Duck curve. Yeah, I'll have to have a look because I've not heard the term duck curve before. Maybe it has to do with solar concentrators. Okay, that has to do with the peak demand of renewable energy. Is it that you're trying to know the meaning of duck curve? Let me see. Could you explain it and how to mitigate a duck curve? Let me see the mitigation strategy for duck curve.
If you can't find it or if you never heard about it, that's fine, Marvin. Maybe the students heard from another area or another renewable energy, which is not included here in the presentation. Or if you want that, maybe you want to take some more information and then the answer can be, you can send it to me, then I will forward it to him.
Yeah, I'll send it to you because I think I know what it means, but the mitigation strategy is what I don't really have answers for the mitigation strategy.
It's okay, don't worry. Yeah, it's okay, don't worry. I think last question coming on the chat.
No, is there another question?
Yeah, another question.
Okay, I want to ask
the
about
last
tidal
one.
energy. Yeah, I want to ask about tidal energy. So for this tidal energy, how big is the potential, and how do we know that the places is suitable have potential for tidal energy? Like I said, tides can be predicted all year round. Now the intensity of the tide, it's normally a test. People test. They have what they call FAB tests. So you can drop a device and monitor. You know that the tide is certain. It will definitely rise and fall twice a day. So, but the FAB test helps you to know the intensity of the tide. So you could drop it at different location. So you could tell what the tide is like and whether that location will be suitable for installation of the tidal stream.
Yeah, I think it's clear enough here. Thank you for all your answers and also all presentations. Students, are you happy with today's presentation?
There's another question.
Another question. Okay, this is the last one, yeah? The very last one.
I want to ask about Texas blackout. How is the response lecture about the blackout in Texas? Okay. The Texas blackout, we all read about it on the newspaper and saw what happened. If you have friends or relatives down in Texas, everybody was concerned about the blackout. And it was as a result of extreme temperatures, cold temperatures. And what happened is those are some of the things that modeling can solve. Now that it has happened once, if they are going to install wind turbines in Texas now, they will look at a way to design it in such a way it will be able to stand those extreme temperatures. Because what happened was it got so cold that wind turbines got frozen. It wasn't the wind, they got frozen that they could not rotate. So they failed. And then because of the harsh temperatures, other conventional systems also failed and they could not have power, and they use power for everything. That tells you the importance of power. Power is used for heating. So once there is no power, there was no heating. Once there was no gas supply, there was no heating. And that was the issue in Texas. And now a lot of people have resigned. So the MD of the company has resigned, whether it was human error or not. What was stated in the media is that this thing has happened before in Texas, but they did not take it seriously. So they did not follow on researches to improve on their energy system so that it could stand this kind of condition. And now it came up again. That's why a lot of people had resigned from their position in the company that manages the biggest power company in Texas. That's the main reason. So, and that's what we're talking about. Modeling is very important. Even after modeling, you might not get all you need in your model. But when you do an installation and you begin to have challenges, you need to go back to look at how to mitigate those challenges. This wasn't done in Texas, and hence they had the challenges they had. So it's not like they've not had extreme temperatures before that led to blackout. They have had. It wasn't as bad as the second time. They didn't do anything about it. They felt it's one of those things. And then at the end of the day, it comes again, and it had some people had to be hacked. So it's not like research provides all solutions. It provides solution, and we keep on improving on the solution as we meet challenges every day. If you've not walked a road before, you will not know how long that road is. But if you have, when you're going through that road the second time, you would go through that road better. It is like as you are, if you have to go back to secondary school now that you're in university, I guess you will do better than you did when you first went to secondary school because you now have a clearer understanding. You've walked through that road before. I guess that's the last question.
Yes, I'm afraid that's the last question because we don't have much time left.
That's all right.
Yeah.
That's we've spent almost.
But Marvin, can you accept another question? If they, for example, my student, they can write it to me, then I will forward it to you. Yeah. If
okay, no problem. Any question I would.
So students, if you still have some questions, then
I've learned something. I've learned something today. I didn't. I've not looked into the doc curve before, and I would have to now read.
Yeah, I will forward it to him as well. Okay, but students, if you still have more questions, then please send it to me. Then I will forward to Marvin. Then Marvin will answer it, and then I will give the answer to you. Yeah. So it means that although the presentation ends, but knowledge still continue. Yeah. It means you still have to learn something. You still can learn something, and then you can ask to Marvin or to another expert. Okay. Again. Okay, before I close the session, please give a very big applause to our speaker today. Okay, give a big applause. Thank you, Marvin.
Thank you very much.
Thank you very much for your presentation.
Thank you for listening to my boring lectures.
No way, no. It's very good. Okay, this is very new knowledge for my students. I believe they can improve their knowledge, and also they gain something very good today. Okay, thank you for your kindness to give my knowledge, my students knowledge, new knowledge, and then hopefully that we can they can still listen to your presentation for the next in the future, so that they can get another benefit from your next presentation. Okay. I think I should close the session. Okay. Thank you, Marvin. Thanks again. We will see for another presentation. Thank you.
All right. Thank you. Take care. Bye.
Bye.
Thank you, sir.
Thank you, sir.